In the last class, we have seen PN junction diode and its characteristic curve, that is with the forward biasing how the current rises almost exponentially, and in the reverse voltage when it is applied, current is almost 0 except for the reverse saturation current due to minority carriers. Now, in order to apply it in a circuit, we must get the equivalent circuit for the PN junction diode, that is we have to model the diode electrically. So, we will be now considering the circuit model for a PN diode. Now, the diode equivalent circuit is a combination of elements properly chosen to best represent the characteristics of a device in a particular operating region. So, we have this PN junction which is formed from p-type and n-type materials on silicon or germanium semiconductor, and this is the diode symbol that we have known in the last class. Now, we have to now form an equivalent circuit by a combination of electrical elements, but these components must be properly chosen in order to represent the characteristic which is shown by the diode, and that should be also in the operating region where we are going to apply the diode. So, now how to form the equivalent circuit model for a diode? If we consider again the characteristic of a diode, the forward region we will be seeing this curve which is a non-linear curve up to the threshold voltage 0.7 volt. Due to the barrier potential, current is 0, and as soon as the voltage applied across the diode is beyond or greater than 0.7 volt for silicon, we are taking an example of silicon, the current rises sharply, and this is the characteristic curve, and in the reverse bias of course this is almost 0. That is why it will be coinciding with the 0 line. We do not consider the reverse saturation current because it is in a micron range, very small, it will not be significant. Now, if we study this characteristic curve of the PN diode, we see that this is non-linear and it is not easy to model a non-linear characteristic. So, here we have to do an approximation, that is we will be considering this whole characteristic as a piecewise linear characteristic. Piecewise linear characteristic assumption has to be made in order to correctly model the diode. Now, in this case you see that up to 0.7 volt it is 0, current is 0 and then it is rising. So, we can assume that 0.7 volt up to this voltage it is 0, and then this portion where it is exactly a nonlinear characteristic, but when the current rises after some time you see that it is rising almost linearly. That is why we can approximate this region as a linear characteristic, and the overall characteristic can be basically divided into two regions. One is up to 0.7 volt when the current is 0, and then a linear characteristic which will be determined by the slope. The average resistance of this diode is, as we know, it is the reciprocal of the slope. The slope is actually the y by x, and we will be finding out the average resistance by taking its reciprocal. It is because it is voltage by current. Now, this average resistance of the diode is to be known. If we know that two operating points, then we can find this out. So, now we will be approximating this as this piecewise linear characteristic, where this average resistance of the diode is to be found out. So, now if we know one point which is say 0.8 volt and 10 milliampere in the operating region. That is, the point can be known from the data sheet which says about the voltage and current levels for a particular operating point. If we know one point, then it is enough to find out this average resistance, because our average is del V D by del I D, that is the change of the rate of change of voltage by rate of change of current between two operating points. So, one operating point, if we know, at this operating point if we know the voltage, say it is known as 0.8 volt and current is 10 milliampere, which can be known easily if we see the data sheet of a diode, particular diode that we are using. And the other point obviously can be taken as this point where the voltage is 0.7 volt and the current is 0. This is just the threshold point after which the current rises. So, as this region is linear, that we are approximating by piecewise linear approximation, we can find from these 2 points the average resistance that can be found out if we divide the change of voltage by the change of current between these 2 points. So, one point is this one point is this one. Here the voltage is 0.8 volt and this threshold voltage up to which the current is 0 is 0.7 volt. So, this difference is 0.8 minus 0.7 volt divided by, at this point the current is 10 milliampere and at this point the current is 0. So, this difference between the currents at the respective points is 10 milliampere minus 0 milliampere, which is nothing but 10 milliampere. So, we get this ratio between 0.1 volt divided and the 10 milliampere, that will give us 10 ohm. So, the average resistance for this particular case we can find out as 10 ohm. So, this is the average resistance, or the order of this resistance of a diode is around this ohm, that is it will be in the order of ohm. So, here we have got 10 ohm. So, now the information of this average resistance and this cut-in voltage or threshold voltage, which is 0.7 volt around for silicon and 0.3 volt for germanium. So, these two things are enough information to model the diode, that is the cut-in voltage and this average resistance. So, now the piecewise linear model of the diode forward characteristic is giving us the equivalent circuit representation, which is shown here in figure B. This figure A is the piecewise linear model. This VDO means this is the threshold voltage or cut-in voltage or because of barrier potential. So, up to this the current is 0 and then this is a piecewise linear approximation that we have done, where the slope of this line is 1 by RD. This is the average resistance of the diode. So, this straight line is having a slope of 1 by RD. That is enough for finding out the equivalent model. So, now if we draw the equivalent circuit for this piecewise linear model of the diode, we show it by these two things. One is this cut-in voltage and one is this average resistance, and the direction of conduction in the diode is shown by this ideal diode symbol. This ideal diode symbol is to show the current conduction path, and as this barrier potential or this threshold voltage is opposing this conduction of current in this direction, this opposition is shown by this battery, which is VDO, that is this barrier potential or threshold voltage or cut-in voltage. The same name denotes this cut-in voltage only, different names are used for this voltage, and this is the average resistance. So, this part is, this whole part will be the diode's representation, and in an electrical circuit we denote it by this model. So, this is VDO, you know, that is 0.7 volt around for silicon, and this average resistance, of course, we have to find out given two operating points we can find this out, and this ideal diode is just to symbolize this direction of conduction of this diode. So, this model we have found which will be representing the characteristic of the diode, of course, in the piecewise linear approximation. Now, another approximate model which will be coming from this model, again we can further approximatize is, you can further simplify this model which will be giving rise to constant voltage drop model. So, this model is constant voltage drop model because of the fact that in most of the circuit applications where you generally apply a diode, you will find that the resistance of the diode is quite small as compared to the other elements of the network. So, we can ignore this resistance of the diode without violating much, and this assumption will be used for further simplification of this piecewise linear model, which gives rise to the constant voltage drop model. So, in the constant voltage drop model, that means we do not have this average resistance of the diode into consideration, we do not take that into consideration and we ignore this. That means R D is ignored and it is made 0. So, we have in the characteristic, if we now see, there will be this 0.7 volt for silicon, which is the threshold or cut-in voltage, and the characteristic curve will be rising vertically because this resistance is 0, it will be rising to infinitely high current, and this is the representation we get after simplifying the piecewise linear model with the assumption that R D is 0, which can be ignored or neglected. So, our now new characteristic which will be boiling down from this earlier piecewise linear model is this one. Now, to represent this model, we have only to represent it with this cut-in voltage, which is 0.7 volt for silicon, and of course, this ideal diode will be there to denote the flow of the current while the diode is conducting. So, here this R D will be absent. So, this is the simplified or constant voltage drop model, and this model is very much used in practical circuits, and here of course, this resistance is not there. So, the model becomes very simpler, and in the cases where the calculation of current is not so much important and only the application of diode is important, that is for example, in rectifier circuits where we are concerned about the effect of using the diode, not the exact calculation of the currents as such, then we can use this model, and this is mostly used in those cases. And that is why, that means we are getting now equivalent circuits, 3 equivalent circuits, that is one is the ideal, of course, ideal assumption where the characteristic will become like this, that means it will be 0 up to when the applied voltage is reverse biasing the diode, it will be totally 0 current, and when it is just increases beyond this 0, that means we apply forward bias, the current will rise immediately to infinite value and there will be no voltage drop across the diode. So, this is the ideal equivalent circuit for the diode. And other model which we have just now found is piecewise linear model. So, in this case, this characteristic will be obtained up to cut-in voltage V T, that is the threshold voltage 0.7 volt for silicon, the current will be totally 0 and then it will be rising, and the rise of this current will be determined by the slope, that is the average resistance, which is the reciprocal of the slope. This average resistance will determine the rise of this current. So, the current will rise as per the slope given by this average resistance. So, this is the piecewise linear model. So, this is first model. Another model we have got and further simplification for this from this piecewise linear model will be the constant voltage drop model. It is approximate equivalent circuit from the piecewise linear model. So, in this constant voltage drop model we have the cut-in voltage 0.7 volt and the ideal diode will be denoting the conduction part of the diode. So, now in the diode circuit analysis, when you will be applying a diode in an electrical circuit having other components as well. So, the diode will be in the on state if the current established by the applied sources is such that its direction matches to that of the arrow in the diode symbol, and if the voltage applied across the diode is greater than or equal to 0.7 volt for silicon and 0.3 volt for germanium, then the diode will be on. So, in a circuit when we apply the diode, we have to see how much voltage is being applied across the diode and in what direction. So, whenever it is beyond 0.7 volt for silicon and 0.3 volt for germanium, then the diode will conduct and the direction of current will be given by the direction of the diode current when it is in the on state, that we can find out. Now, if we now consider a diode circuit, a very simple diode circuit, let us take having an applied voltage VDD, that is a battery, and this circuit is having a diode and a resistance R. This resistance is external resistance. So, this series circuit if we consider, now the approach which is used for analyzing diode circuit graphically, it is called load line analysis. That means, we will have to draw a load line. This load means the resistance, if we consider only resistance as the component which is connected across this in the diode circuit, then it will be the load will be only resistance, and for simplicity we will be considering a resistive circuit, and of course, this is a DC circuit. So, only the component which will matter is resistance. And if we now consider the series circuit and we will be analyzing this circuit graphically, drawing a load line. Now, how the load line can be drawn? What is the way of drawing this load line? That we will be discussing first. So, in this series circuit, if we now apply the Kirchhoff's voltage law, which is the law applied to a series circuit, and all of us know what is Kirchhoff's voltage law. The algebraic summation of the voltage drop in this loop is equal to 0. So, that law if we apply now, in this circuit we will be getting VDD minus ID into R. ID is the current in this circuit, diode current, and minus VD, the drop across this diode, is equal to 0. It is coming from this Kirchhoff's voltage law being applied here in this circuit. So, simplifying this, we get VDD equal to ID R plus VD. Now, in this equation, if we now set VD equal to 0, we get the maximum diode current that can flow in the circuit given by ID equal to VDD by R. So, that will be one extreme point, that denotes the maximum diode current that can flow in the circuit. And if we make ID equal to 0 in equation 1, this equation if we make ID equal to 0, then we get the maximum voltage that is across this diode. So, that is VDD, VD equal to VDD. Now, these 2 points will be defining a straight line, because in order to draw a straight line we need only 2 points, and this straight line is called the load line. And if we now draw the characteristic curve and superimpose on it the load line, then there will be a point of intersection between these two graphs, and that intersecting point will be the point of operation of the system. That means, we can find the point of intersection and that point will denote the point of operation for this circuit. So, let us take an example and see. Before that, this is the characteristic, diode characteristic, this curve, exactly this plot will be the diode characteristic, nonlinear characteristic. Now, we draw the load line in the same plot, the same graph. These 2 points, one is VDD, one extreme point, and the other is VDD by R, the other extreme point for this load line. Connect these 2 points and we get this straight line. Now, this straight line and this characteristic curve, they are intersecting at this point, which is the Q point. It is called the Q point or quiescent point, or it is silent point. It is, or it is also called the still point. Meaning that it is a DC voltage is applied. If a small signal voltage is applied along with the DC, then the Q point will shift up or down, but here will be the only DC condition, and that will be called the silent point or Q point. So, this is the operating point for your circuit. So, now if I project it on this from this Q point, if I project on the x and y axis, that is this voltage and current axis, I get these 2 points VDQ and IDQ, and these 2 points will determine exactly the Q point. What is the Q point? That point is determined by this voltage VDQ and the current IDQ. So, I know now the operating point having this voltage across this diode and the current through this circuit or the diode is IDQ. Now, if we change this resistance in the circuit, then of course, this slope of this load line will change. We will be getting a different load line giving a different Q point. For example, now if I consider a circuit, a series diode circuit given in figure 1, here the applied voltage VDD is 10 volt, resistance applied in externally in the circuit is 1 kilo ohm, and this is the diode, which is a silicon diode, it is mentioned here. Now, this diode which is used in this circuit is having this characteristic given by the figure 1b. This is the characteristic curve of the diode. So, you can see that after 0.5 volt it starts to rise, the current starts to rise, and at 0.8 volt it has 10 milliampere current flowing through it. So, this characteristic curve is given to you. Now, for this circuit, employing this diode characteristic, you have to determine the Q point as well as the voltage across this resistance VR. These two are to be found out. So, now for that, again first of all you have to find out the 2 extreme points of the load line. So, as we have already seen, the extreme current ID max will be given by VDD by R when you make this voltage drop across the diode 0, and for this particular example it is 10 volt by 1 kilo ohm. So, it is 10 milliampere, and VD max, this voltage can be found out making this ID 0, that is given by the applied voltage VDD. So, this is 10 volt. So, these 2 points are known now. We can now draw the load line. Let us do that. So, this load line is drawn. You see one point is 10 volt VDD max, maximum VD, and this point is ID max, that is VDD by R, which is 10 milliampere. Connecting these 2 points, I get a straight line. This is the load line, which is drawn along with this characteristic curve. So, as you can see here, the point of intersection between this characteristic curve and this load line is Q. So, now if I now project vertically from this Q point, I get the point of intersection with the VD axis at around 0.8 volt. Of course, this has to be in scale. I mean, this whole plot has to be drawn to scale, only then the exact point of intersection can be found out, otherwise there will be an error. Now, if I project it on the other axis, current axis, here it intersects at around 9.25 milliampere. So, the point is defined, this Q point is defined by 0.8 volt and 9.25 milliampere. So, this is the operating point. That means, this circuit current at that particular operating point is 9.25 milliampere and the voltage across this diode is 0.8 volt. Now, what about the voltage VR? That has to be found out. So, the voltage VR, as you can see in this figure, this voltage drop is the current flowing through this resistance multiplied by this resistance. So, current flowing through it is IDQ at that particular operating point and multiplied by resistance 1 kilo ohm, we get this VR, that is equal to 9.25 milliampere into resistance 1 kilo ohm, which is 9.25 volt. Now, this is one way of finding out VR, but another way also we can find out this VR. This VR is nothing but this voltage minus this drop. So, there is another way, both the ways should actually match. If we correctly measure this graph, this should be same. So, VR is equal to VDD minus VDQ. So, 10 volt minus 8 volt is 9.2 volts. Now, you can see there is a difference, but ideally if we measure the graph correctly, both will be same. So, this error comes because there is an inaccuracy in reading the graph. So, when you measure it to scale, it should be same, both the results should be same. Ideally, that should be same in both cases. Now, in this whole analysis, we have seen that it is very important to draw the characteristic curve, measure everything accurately. Now, that is tedious, or in some cases you do not really need so much of accurate calculations. So, we can also use an approximate equivalent model for a diode. That is, if we consider again this characteristic curve which is non-linear, that exact characteristic curve which is this one, but this can be approximated by that piecewise constant voltage model. Constant voltage model, we have seen that 0.7 volt is the cut-in voltage. So, now if I use that model, instead of this whole non-linear characteristic curve, it is very difficult to accurately measure and it is not needed also. So, we draw this approximate equivalent characteristic, that is 0.7 volt, and it is current is rising infinitely at this point. After 0.7 volt is overcome, it is rising infinitely, that is the approximate equivalent model. Then let us see where is this point of intersection lying. So, here we can see that Q point is defined by 0.7 volt and this current is also found to be 9.25 milliampere. So, this is the operating point we have got using approximate equivalent model. So, using approximate equivalent model, whatever Q point we have got, that is not very much different from using exact equivalent circuit, because here of course earlier we got this voltage is 0.8 volt, but here we are getting 0.7 volt, but the current is same. So, in this case we can see very clearly that using approximate equivalent model will also serve our purpose, and where this exact calculation of current is not required or exact calculation voltage is also not required, we can very well approximately use this we can use this approximate equivalent model and carry on our analysis. So, you will be finding that in most applications this approximate equivalent model or constant voltage model is used. Now, what will happen if we use ideal model, ideal diode model? Then of course, this will be current will be rising at 0 point itself and the point of intersection will be at 10 volt. Of course, this is quite different than these results of approximate equivalent circuit, because if I consider this line and find out this intersecting point, the intersecting point is at 10 milliampere, sorry not 10 volt, 10 milliampere. So, 10 milliampere intersecting point current point we get and voltage is 0, whereas in this case we have seen 0.7 volt and 9.25 volt. This is very much different from what we will be getting in ideal model. So, ideal model is practically not very much usable, and that also we will be using only when we just have to know the current conduction part. Then in that case we can use the ideal model. So, effectively we will be using mostly the approximate equivalent model. But this is of course what we are considering, it is about the DC signal, DC constant voltage. But what will happen if we have a small signal, AC signal superimposed on the DC voltage? Then of course our whole model will have some extra terms, not only the resistance, because whenever this change occurs in the voltage, then capacitance effects will come. So, there are two capacitance effects which will be present in a diode, those are known as the junction capacitance and the diffusion capacitance. So, junction capacitance basically is related to the space charge region, and a capacitance will be developed in the space charge region when the voltage across this space charge region or depletion region changes. Now, let us consider again the p-n junction, go back to p-n junction, and what will be the depletion layer width that we already know in an open circuit at p-n junction. This will be the depletion layer width given by this expression that we have earlier discussed. Now, if we have forward bias this p-n junction, as we know that this majority charge carriers, they will be repelled by this holes will be repelled by this positive terminal and electrons will be repelled by this negative terminal. So, they will be coming towards the junction, and in the process they will be neutralizing these ions, and as a result of which the depletion layer width will be reducing. That means, there will be less uncovering of the fixed charges. So, the depletion layer width reduces, and the depletion layer width will be now given by, in the expression earlier expression of open circuit, we will be having, instead of VBI we will be having VBI minus VF, because the potential barrier is now reduced, the potential hill is reduced by this voltage. So, as you can see, the depletion layer width is reducing, and if we consider the reverse bias case, the depletion layer width will be more, since more and more charge carriers will be attracted by this positive and negative terminal of the reverse bias. Electrons will be attracted away from the junction, holes will be attracted by this negative terminal away from the junction. So, uncovered charges of the ions will be more and more. So, charges will be more here, uncovered charges, and earlier the depletion layer width also will be affected, because now the voltage across this will be not VBI, VBI plus VR, this potential hill is now increased. So, now this is like, if you now visualize this width, there are charges on the right positive, there are charges on the left negative, which are fixed charges, and the charges are now the charges are changed, the number of fixed charges are changed by this forward and reverse voltage, because forward voltage will be reducing the number of charges accumulated on the depletion layer, and the reverse bias will be charging, causing more charges. That means, it is like a charging and discharging taking place along across a capacitor. So, if we consider it as a parallel plate capacitor, we can visualize it as a parallel plate capacitor having the width between the two plates, as if these are two plates, and width between these two plates is W depletion, and we have this in between material silicon, and so it is like a parallel plate capacitor, which is given by C is given by ESA by W depth. That means, it is given by the ES is the permittivity of silicon, A is the cross sectional area of the junction, which is of course perpendicular to this plane of the paper, and this is the W deep is the depletion layer width. So, if I substitute these values, I already know what is W deep. If I substitute these values, then for reverse bias PN junction, I am taking this case specially for reverse bias PN junction, because this junction capacitance will be dominant for reverse bias PN junction, not for the forward bias PN junction. So, this will be giving me after replacement the whole expression comes like this. And now, in the denominator in the numerator, if we consider this whole term, I can replace it by Cj0, means the capacitance when applied potential is 0, open circuit. So, the whole term will be Cj will be Cj naught by root over 1 plus Vr by Vbi. This expression is just found out after simplification of this and replacing this above or the numerator part by Cj naught. So, we get a junction capacitance given by this. So, here Vr is the reverse bias potential, reverse bias or reverse voltage. This is the open circuit built in potential. So, this is called junction capacitance or transition capacitance also. This is very prominent in the case of reverse biasing PN diode. And there is another diffusion capacitance which is prominent for forward bias PN junction, and this diffusion capacitance CD is the rate of change of injected charge with voltage. And so, we get that if we consider the small signal model of a diode apart from the resistance, average resistance, there will be two other factors, one is junction capacitance, one is the diffusion capacitance. So, the overall circuit representation for small signal model will be this resistance Rd, small rd to denote that it is small signal resistance, and Cj, Cd, these two are the capacitances, junction capacitance and diffusion capacitance. So, now we have this small signal model. When you have a small signal along with the DC voltage, suppose I am applying, then we have to consider this model. But for the time being, we will be concentrating more on the DC voltage applied only. So, now let us do an example. You have a circuit given by this two there are two resistances, two diodes. You have to find out this current flowing through this diode D1, current flowing through this diode D2, as well current flowing in this through this resistance R1 and current flowing through this resistance R2. The voltage applied in the circuit is 20 volt, and it is given that the diodes are made of silicon. This information is important for finding out the cut-in voltage, and you are told that you have to assume constant voltage drop model of the diode. So, constant voltage drop model will have this cut-in voltage, as it is silicon it will be having 0.7 volt cut-in voltage, and there will be no resistance considered in the diode, since the constant voltage drop model does not have the resistance in its model, that means it is ignored. So, let us now solve this example. So, we again draw the circuit. Here this voltage is given 20 volt, and this diode 1 D1, D2, R1 is given as 3.3 K ohm, R2 is given as 5.6 kilo ohm. What will be the currents? ID1, ID2, IR1, IR2. This is the problem. You have to use constant voltage drop model. Now, first thing is to find out whether the diodes will be conducting or not. Now, as you can see, this 20 volt is applied, which will be forward biasing these diodes, and so this diode will be conducting. When the diode conducts, this will be 0.7 drop will be there, but then it will 19.3 volt will be available across this. I mean, this diode will also be conducting. So, both these diodes are conducting. So, that means we have now the current flowing in this diode also, this diode also. So, for that we have to now find out what will be the current. So, now the drop across this D1, which is VD1, say the drop voltage drop across D1 diode, and its constant voltage drop model, so 0.7 volt. Similarly, VD2, that will be also 0.7 volt. These two diodes are made of silicon, so they are same drop across them. So, now if we consider now the voltage drop across this resistance R1, this voltage drop between these 2 points is 0.7 volt. So, if we know this volt divided by this resistance 3.3 K, I can find the current IR1. So, IR1 is equal to VD2 by R1, and VD2 is 0.7 volt divided by 3.3 K ohm. So, this will be giving, this calculation will give you 0.212 milliampere. So, one current we have found out, that is IR1. Now, in this circuit, this part, this Kirchhoff's voltage law is applied. If we apply Kirchhoff's voltage law in this loop, that is 20 volt minus VD1, that is the drop across this diode, minus VD2 minus VR2, where VR2 is this drop, we get the KVL, Kirchhoff's voltage law, being applied. Use KVL in this loop, then using KVL we get 20 minus VD1 minus VD2 minus VR2, that is equal to 0. Everybody knows Kirchhoff's voltage law. What is it? Algebraic sum of the voltages around the loop is 0. So, we are just simply applying that. Now, you substitute VD1, VD2, that you know. So, 20 minus 0.7 minus 0.7 minus VR2 is equal to 0. So, what is VR2? We can now find out. 20 minus 0.7 minus 0.7, that is equal to 20 minus 1.4, and this is 18.6 volt is available across this resistance R2. So, now if I know this voltage, I can find this current IR2. What is this current? For VR2 divided by R2. So, IR2 is equal to VR2 divided by R2. Just substitute these values. 18.6 volt divided by R2 is given as 5.6 K. So, that will be 3.32 milliampere. This is the IR2. Now, what is left to find out? Let us see, ID1 is to be found out. This we have, ID2 we have also to find out. So, these currents are, we have found out IR1 and IR2 we have found out. Now, this current ID1 is same current IR2, because you see here the current which is leaving this positive terminal of this battery must enter this positive and negative terminal of this battery. So, ID1, the current which is coming out from this terminal is ID1. So, the current which is entering this terminal is IR2, this must be equal. So, your ID1 is nothing but IR2. IR2 we have already found out, and that is equal to 3.32 milliampere. Now, what is left is ID2. So, this current ID2 has to be found out. Now, come to this point and you apply Kirchhoff current law to this point. So, Kirchhoff's current law says that the sum of the incoming and outgoing currents at a node is equal to 0. So, what are the incoming currents and outgoing currents at this node? Incoming current is ID2 that we have to find out. Another incoming current is IR1, this is IR1, and outgoing current is IR2. So, this algebraic sum must be equal to 0. So, IR2, that is if we follow this rule of entering current and leaving current are having opposite signs. So, this leaving current is say positive IR2, entering current IR1 and ID2 are negative. Then we get IR2 minus IR1 minus ID2 equal to 0. So, what is ID2? That is the question. We have to find out ID2, that is nothing but IR2 minus IR1. So, IR2 and IR1 we already know, 3.32 milliampere minus IR1 is 0.212 milliampere, these two we have found out. So, this subtraction will lead to 3.108 milliampere. So, all the currents are now known. So, this example we have used constant voltage model. Now, let us do another example, try to solve this problem. So, in this circuit shown in figure 2, determine the current ID, the current which flows through this diode, if the voltage V1 is given as 10 volt, V2 is given as 15 volt, and assume the diode drop to be 0.7 volts. So, that means here also you use constant voltage drop model, because you have to neglect forward resistance of the diode. So, this circuit, in this circuit we have to find out ID. So, now here we have to first of all examine what is the voltage being applied across the 2 points of the diode. This is P, this is N. What voltage will be applied across these 2 points? So, let us try to solve this problem. Again we draw, this is the diode and the resistances are like this is ground, this is ground, this is B2, this is B1. The resistances are 10K, 10K, all are 10K, 10 kilo ohms, and we have to find out this diode. This B1 is equal to 10 volt, P2 is equal to 15 volt. Now, you see what voltage is being applied across this diode. VD will be, VD means the voltage across this diode. If I consider this VD, this voltage, what will be the voltage? This voltage at this side, you have this voltage as 15 volt, and this side it is 10 volt. So, the difference between these two voltages, the potential across these 2 points is 15 minus 10, which is 5 volt. So, VD is 5 volt, and as it is greater than 0.7 volt, so diode will conduct. So, this diode is conducting, and that has been ascertained first. So, now we have to find out this current ID. Now, to find out this current, we will be now taking help of nodal analysis. Let us consider this node and this node, and let us name that this node is A, this node is B. The voltage at this node with respect to ground is VA, the voltage at this node with respect to ground is VB, and the Kirchhoff's current law will be applied at these two nodes. So, now let us now consider the node B and find out according to Kirchhoff's current law. So, the node B, if we consider, apply KCL, Kirchhoff's current law. So, this will be what? Kirchhoff's current law, sum of the incoming and outgoing currents is equal to 0. So, the outgoing current is what? VB minus V2 by 10K, one outgoing current in this direction we are considering, assuming that this is outgoing current is in this direction, VB minus V2 by 10K plus VB minus 0, this is ground, divided by 10K. Another outgoing current is ID. So, summation of all this equal to 0, all are in the same direction, which is the outgoing. So, we write it applying Kirchhoff's law at node B is V B minus V 2 by 10 K. I am just removing K, all are in kilo ohm order. So, I am just omitting this K kilo plus V B by 10 plus I D equal to 0. This is number 1 equation. Similarly, if I apply the Kirchhoff's current law at node A, what will I get? The sum of incoming and outgoing current equal to 0. Now, incoming current is I D, and let us take the outgoing current as V A by 10 K plus V A minus V 1. This is the drop across these 2 points, divided by 10 K will give me this current. So, now this second case, this at node A, if I apply KCL, I get V A by 10, 1 outgoing, plus V A minus V 1 by 10, plus, it will be not plus if I consider the diode current I D, as it is incoming, it will be minus I D, that is equal to 0. This is number 2 equation. Now, we have to solve number 1 and number 2. I write number 1 equation again. What was the equation? V B minus V 2 by 10 plus V B by 10 plus I D equal to 0. So, obviously, I can subtract, I can sum them up and eliminate the term I D, solving for this, solving of this equation. So, this is number 1 equation. So, summing up 1 and 2, I get V B minus V 2 by 10 plus V A by plus V B by 10, this and this will cancel, plus V A by 10 plus V A minus V 1 by 10 equal to 0. So, now again we see that this V 2 and V 1 we know. Another thing we notice here is that what is V A? V B minus this drop is 0.7. So, V B minus 0.7, the diode drop, that is equal to V A, the difference in the potential. So, V B minus this drop is equal to this potential. So, we can now replace this V A in terms of V B minus 0.7, constant voltage drop model we are using, and also we know that it is given V 1 is equal to 10 volt, V 2 is equal to 15 volt. All this if I substitute in this equation, now I can solve it. I will be now having from equation 3, I will be having V B minus V B by minus V 2 is equal to 15. So, V B minus 15 by 10 plus V B by 10, keep V B as V B, I will be substituting V A, plus V A is V B minus 0.7, here I substitute, I want to keep only one unknown, plus V A is V B minus 0.7, so V B minus 0.7 minus 10, V 1 is 10 divided by 10 equal to 0. So, here you see only 1. So, now here only one unknown is there, which is V B. So, now we can very easily solve this. So, it will be further simplified, V B by 10 minus 1.5 plus V B by 10 plus V B by 10 minus 0.07 plus V B by 10 minus, that is 10.7 by 10 is 1.07, that is equal to 0. So, I get 1, 2, 3, 4 V B by 10, and the other side if we do this calculation, I will be getting 2.64. So, that gives me V B equal to 26, this 10 into 22.64 is 26.4 divided by 4, that is giving me 6.6 volt. So, now I get V B equal to 6.6 volt. If I know V B now, I can find out what is I D, because if you look back, what is this I D? If I substitute here in this case, I mean here I can substitute V B, which I have found out So, what will be ID? ID is just transfer all this left side to the right, it will be V2 minus Vb by 10 minus Vb by 10. ID is equal to V2 minus Vb by 10 minus Vb by 10. So, just replace these values, V2 minus Vb by 10, V2 we have already given in the circuit as 15 volt. So, 15 minus Vb we have found out 6.6 volt, right. So, divided by 10 minus again Vb by 10, 6.6 by 10. So, that is what 10 in the denominator and the numerator, 15 minus 6.6 minus 6.6. Do this calculation, it will be giving you the numerator as 15 minus 13.2 by 10. So, you will be getting 1.8 volt in the numerator. In the denominator, you just remember that 10 is 10 kilo ohm actually. I have omitted the kilo in the early stages. So, now voltage by kilo ohm will be giving the unit in milliamps. So, what will be the result? 0.18 milliampere. So, now my ID diode current which I have got is 0.18 milliampere. So, this in this example we have taken help of only the primary basic laws or principles, Kirchhoff's current law, Kirchhoff's voltage law only we have been using. So, in the diode circuits also, I mean whenever you analyze the circuit, all those basic primary laws, fundamental laws of electrical engineering like Kirchhoff's current law, voltage law, nodal analysis, all these will be applied, and the diode should be replaced by its model to fit into the circuit. It is not a physical diode now we will be considering the equivalent, approximate equivalent model of the circuit, that is the electrical circuit which will be representing the diode. So, now today we have learnt about how modeling is done on the physical diode, PN junction diode. Approximate equivalent model of the diode has been derived, which is most commonly constant voltage model that is being used in electrical analysis of this circuits having diode. When you have to only consider the diode as an in application only, that is we are not so much very much concerned how accurately we find out the currents and voltages, that if it is not a prime concern we will be using approximate model, and even approximate then the constant voltage model is the ideal model of the diode, which is of course very basic, and it will be only used for those cases of circuits when the applied voltage is much more or the other components of the circuit is much higher in values than the resistance of the diode. Then we will be ignoring the diode resistance, we will be only considering the ideal model of the diode without considering the cut-in voltage as well as the resistance. Only we will be using it as a switch, like it is either conducting or non-conducting. In that aspect we will be using ideal diode, but generally we use constant voltage model. So, we will use this model, constant voltage model, as well as the ideal model, as well also the linear, piecewise linear model of the diode. If it is mentioned what is the average voltage, average resistance, it is mentioned, then we will be using the piecewise linear model. If the compulsion is there that we have to use the average resistance also, otherwise we will be sticking to the constant voltage drop model of the diode, and we will be next going into the detailed discussion on application of diode in the circuits like rectifier circuits, etc.